people tend to use cameras as the name for these things, but it's extremely misleading because it gives the impression that that what you're doing is just building something that most people can buy in MediaMarkt or into Discount or Saturn, In fact, they're telescopes with rather high resolution imaging. What we decided to do was to make our camera a little bit special by having not merely high resolution, but also performing stereo observations and in full color. HiRISE, the American Mars camera, covers a swath width of about 1.2 kilometers on the planet when it takes an image. We can go much larger than that. We go to about 9.5 kilometers so that we can get much better color context for our targets. The other thing that we can do is that we have a rotation mechanism which allows us to make stereo in one pass over the target. It's quite a challenge to build one of these instruments in such a very short period of time. We're basically trying to build an instrument that would normally take, people say, 38 months to build an instrument of that sort, and we were trying to do it in 23. It was very, very tight indeed. We certainly were under a lot of pressure. There were times then when we were really getting worried. It was really getting nervy. But the team pulled it through. They really managed it. The really hot topic at the moment is looking at these signs of what we believe to be liquid water on the surface. So there appears to be something that's giving the impression that there is some melting, and then you're creating sort of dark traces along the surface. It almost can't be anything else. It has to be liquid water seeping along the surface. But we'd like to be able to use CaSSIS to try to look at variations of this phenomenon over local time. Here we can take advantage of the fact that the trace gas orbiter is not in a sun-synchronous orbit, and therefore we can observe these places at different times of day, which might be very useful in trying to constrain the properties of these areas. The other thing that I'm interested in getting at is to look at various dynamical phenomena associated with what we refer to as phase transitions. So sublimation and condensation of ices on the surface. Well, the most important thing that we have to do after the assembly of the instrument is to perform a series of tests. Now, we have a number of tests that are called environmental tests. And these typically simulate the environment that the instrument is going to see. Now, the first thing that it sees is that it's sitting on this rocket and it's getting shaken to bits, right? And so we have to make sure that the instrument can withstand that shaking. And we'll be sitting on a proton rocket, and these things shake quite a lot. And so we have a shaker table down here at the University of Bern in what we call our Gross Labor. And the first thing that we do is that we stick our instrument on this shaker table and simulate the proton launch.
Well, I had to round it. And 184, 9.73.
The next thing that we do for environmentals is that it's going up into space. And so we put the instrument into a vacuum chamber and we heat it up and we cool it down. And then we test to see whether the instrument can withstand all of that and still operate correctly and function correctly. We actually discovered a small problem with CaSSIS when we did that. There was a sort of a rotation bearing that was being clamped as the temperature went down. And so the little motor that's inside the rotation mechanism wasn't strong enough to rotate against this friction. And then we had to figure out a way to solve that. And so we did a little bit of surgery because we just had no time to take the entire instrument apart again. So we used various endoscopes and little bits of razor blades and whatever, and did a sort of a bricolage, as the French say, But it worked. It was very successful, and now the thing rotates perfectly.
Let her go, babe.
Okay, sending down.
And those are all part of our testing before we then deliver the instrument to the spacecraft. It's sort of maybe a little bit surprising, but we basically put it in a truck. We have to put it in some fairly large boxes, which are and on a special table, so that it doesn't get shaken around too much when we're driving it down the road. But in fact, what we did was that we put it into the back of a rented truck, and set it off at 6 o'clock in the morning and drove it to Cannes in the south of France to be integrated to the spacecraft. And a few days later, it was bolted onto the spacecraft, and there it was, part of the TGO spacecraft, fully integrated. Proton does have a failure rate that is perhaps not as high as 1 in 10, but not so far away. And so there's a chance that it won't make it. On the other hand, I think I'm quite proud of what we've managed to achieve in getting the instrument to the spacecraft. And I think the team has done a tremendous job in doing that.